I know what you're thinking, clickbait. Everyone knows gravity is 9.8 meters per second squared. We drop things all the time. And the speed of light, 299,792,458 meters per second. Done. Simple, right? But what if, and this is real, we've never actually measured the speed of light in just one direction? What if we've only ever measured its round trip? Think about it. Every time scientists measure light speed, they send it from point A to point B and back to point A. They time the entire journey, divide by 2, and call it the one-way speed. But that's like timing a car trip to the store and back, then assuming traffic was the same in both directions. Picture this. You're holding a stopwatch. A beam of light shoots out from right next to you, travels across the room, bounces off a mirror, and comes back to you. Click. You stop the timer. The light took, let's say, 10 nanoseconds for the whole trip. So you conclude each direction took 5 nanoseconds. But wait, what if the light traveled super fast on the way there, taking only 2 nanoseconds, and super slow coming back, taking 8 nanoseconds? You'd never know. Your total time would still be 10 nanoseconds. This isn't some thought experiment dreamed up by bored physicists. This is a real limitation that has puzzled scientists for over a century. We've built our entire understanding of space and time on an assumption. An assumption that light travels at the same speed in all directions. But we've never actually proven it. Every laser experiment, every measurement between Earth and the Moon, using those reflectors the Apollo astronauts left behind, every GPS satellite calculating your location, they all depend on light making a round trip. We've gotten incredibly good at measuring that round trip time. But the one-way speed, that remains one of physics' greatest unsolved mysteries. So buckle up, because we're about to dive into a rabbit hole that challenges everything you thought you knew about the fundamental nature of reality itself. Let's start with what we actually know versus what we think we know. The official speed of light, that famous number carved into the foundations of physics, is based entirely on round-trip measurements. Not a single experiment in the history of science has directly measured light traveling in just one direction without making assumptions first. This might sound impossible, but it's absolutely true. Every method we've ever used involves light making a complete journey from one point back to the same point. Take the most basic laser experiment that students perform in physics labs around the world. Scientists shoot a laser beam at a mirror placed exactly 1 meter away. The light travels to the mirror and reflects back. They measure the total time for this 2-meter journey and divide by 2 to get what they call the one-way speed. But here's the fundamental problem that shakes the very foundation of physics. Dividing by 2 assumes the light took equal time in each direction. It's like assuming your morning commute to work takes the same time as your evening commute home. Anyone who's ever sat in rush hour traffic knows that's not always true. Traffic flows differently at different times. Construction blocks one direction, but not the other. Weather affects visibility in ways that aren't symmetric. The same could be true for light traveling through space. The same limitation applies to every sophisticated measurement we've attempted throughout the entire history of physics. When NASA measures the distance to the moon using those retroreflectors left by the Apollo astronauts during the moon landings, they're timing light's round-trip journey. The laser pulse travels from Earth to the moon, bounces off the reflector, and returns to Earth. The entire measurement depends on that return journey. They fire incredibly powerful laser beams from observatories on Earth, wait for the light to make the 768,000-kilometer round-trip journey through the vacuum of space, and measure the total time with atomic precision. Then they divide by 2 and assume each direction took exactly half the time. This lunar laser ranging experiment is one of the most precise measurements in all of science. They can detect changes in the Earth-Moon distance of just a few centimeters. But despite this incredible precision, they're still measuring a round trip. The assumption that light travels at the same speed from Earth to Moon as from Moon to Earth is built into every calculation. Even our most precise atomic clocks and the timing systems that run the entire internet rely on this same fundamental principle. When scientists synchronize clocks across different locations, they send light signals back and forth, always measuring the complete round-trip time. Think about the global positioning system that guides everything from your smartphone to military missiles. Your phone calculates its location by measuring how long radio signals take to travel from multiple satellites orbiting 20,000 kilometers above Earth. But even this incredibly sophisticated system relies on the assumption that signals travel at the same speed from satellite to phone as from phone to satellite. The GPS system depends on timing so precise that it has to account for Einstein's relativity. The satellites experience time dilation because they're moving fast and experiencing weaker gravity. Engineers have to program the satellites to run their clocks slightly slow to compensate. But all of these relativistic corrections still assume that light travels at the same speed in all directions. Consider the Michelson-Morley experiment, one of the most famous physics experiments ever conducted in 1887. Albert Michelson and Edward Morley were trying to detect Earth's motion through what they thought was a light-carrying medium called the luminiferous ether. Their apparatus sent light beams in different directions and compared the round-trip times. They built an incredibly sensitive interferometer that could detect tiny differences in the time light took to travel back and forth along perpendicular paths. The experiment used mirrors mounted on a massive stone slab floating in mercury to eliminate vibrations. Light from a single source was split into two beams, traveling at right angles to each other. Each beam traveled several meters to a mirror and back. If Earth was moving through the ether, the light traveling in the direction of Earth's motion should take longer for its round trip than light traveling perpendicular to that motion. They found no difference, which helped Einstein realize that the speed of light is the same in all reference frames. But notice something crucial. Even this groundbreaking experiment that helped lay the foundation for Einstein's theory of relativity could only measure round trips. They never measured light going in just one direction. The null result that puzzled physicists for decades was based entirely on comparing round trip times. The pattern repeats everywhere you look in physics and engineering. Radar systems measure round trip times to detect objects. Air traffic control tracks airplanes by sending radio waves that bounce back from the aircraft. The radar pulse travels from the antenna to the plane and back again. The system measures the total time and calculates distance based on the assumption that the radio waves travel at the same speed in both directions. Sonar works the same way underwater. Submarines and ships send out sound pulses and measure how long they take to bounce back from objects. Even though sound travels much slower than light, the same principle applies. The measurement is always a round trip. Fiber optic communication networks that carry internet data around the world are calibrated using round-trip measurements. Engineers send test signals through the cables and measure how long they take to travel from one end to the other and back again. The entire global internet infrastructure is synchronized based on the assumption that light travels equally fast in both directions through optical fiber. Even the definition of fundamental units depends on this assumption. The meter, the basic unit of length, is defined as the distance light travels in a vacuum in 1/299,792,458th of a second. This definition assumes that light travels at a constant speed in all directions. If light went faster eastward than westward, our measuring sticks would be different depending on which direction we pointed them. Here's what makes this truly mind-bending and keeps physicists awake at night. We've never actually verified that light travels at the same speed in opposite directions. We've simply assumed it does because that's the most convenient assumption to make. It allows our equations to work out neatly and our theories to remain mathematically elegant. But assumptions, no matter how reasonable they seem or how well they work in practice, are not the same as measurements. And in science, the difference between assumption and measurement can be the difference between truth and illusion, between understanding reality and living in a carefully constructed mathematical fiction. The reality is that every time we think we're measuring light's one-way speed, we're actually measuring something else entirely. We're measuring an average. We're measuring a round trip. We're measuring everything except the one thing we actually want to know. It's like trying to determine the temperature of a room by measuring the average temperature of two different rooms and assuming they're the same. This isn't a failure of our instruments or our cleverness as scientists and engineers. Modern physics has achieved incredible precision. We can measure distances to within fractions of the width of an atomic nucleus. We can detect gravitational waves from black holes colliding billions of light years away. We can manipulate individual atoms and control quantum states. But we cannot measure the one-way speed of light. This is a fundamental limitation built into the very nature of measurement itself, and it leads us to one of the most profound and unsettling questions in all of physics. If we can't measure the one-way speed of light, how do we even define what we mean by the speed of light? What does it mean to say light travels at 299,792,458 meters per second if we've never measured that speed directly? Think about what this means for everything we think we understand about the universe. Every calculation involving the speed of light, every prediction about how long it takes for light to travel from distant stars to reach our telescopes, every assumption about simultaneity across vast distances, all of it rests on this single, unverified assumption that light travels equally fast in all directions. The implications stretch far beyond academic physics into every aspect of modern technology. The GPS system that guides your car relies on precise timing calculations that assume light speed symmetry. The satellites need to know exactly when they sent their signals and exactly when your phone received them. But this entire system is built on the assumption that radio waves, which are just another form of electromagnetic radiation like light, travel at the same speed in all directions through space. The internet depends on fiber optic networks calibrated using round-trip measurements. When you click on a website, data packets race through undersea cables and terrestrial networks at nearly the speed of light. The entire global communication system is synchronized based on the assumption that light travels equally fast in both directions through optical fiber. If this assumption is wrong, our timing calculations are off, and the whole system could theoretically fall apart. Financial markets depend on split-second timing for high-frequency trading. Millisecond differences in communication delays can mean millions of dollars in profits or losses. These systems are calibrated, assuming symmetric light propagation. Stock exchanges spend enormous amounts of money to minimize communication delays, but they can only measure round-trip times when calibrating their networks. Scientific instruments that probe the deepest mysteries of the universe rely on this assumption. When astronomers observe distant galaxies, they calculate how long ago the light left those galaxies based on the assumption that light travels at a constant speed in all directions. If light travels faster in some directions than others, our understanding of the age and structure of the universe could be fundamentally wrong. The Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories around the world measure the redshift of distant galaxies to determine how fast they're moving away from us. This tells us about the expansion of the universe and the existence of dark energy. But all of these calculations assume that light from those galaxies travel to us at a constant speed. Particle accelerators like the Large Hadron Collider synchronize their operations using timing systems that assume symmetric light propagation. When protons collide at nearly the speed of light, physicists need to know exactly when and where the collision happened. The detectors are synchronized using light signals, and the entire system assumes those signals travel at the same speed in all directions. What if we've been building our entire understanding of space and time on quicksand? What if the most fundamental assumption in modern physics is just that, an assumption? What if there's a whole layer of reality we've never been able to access because we've been looking at it through the lens of round-trip measurements? The more you think about it, the more unsettling it becomes. We live in a universe where one of the most basic questions about the nature of reality cannot be answered through direct measurement. We can split atoms and peer into their internal structure. We can detect gravitational waves from black holes colliding billions of years ago, ripples in space-time itself that are smaller than 1/10,000th the width of a proton. We can photograph the event horizon of a black hole 40 million light-years away. We can measure the temperature of the cosmic microwave background radiation, the afterglow of the Big Bang, to incredible precision. We can detect individual photons and manipulate quantum states in ways that would have seemed like magic just decades ago. But we cannot measure how fast light travels in one direction. This fundamental limitation reveals something profound about the nature of reality itself and the limits of human knowledge. This brings us to a startling realization that challenges everything we think we know about the universe. The speed of light that appears in textbooks, the speed that defines our understanding of space and time, isn't actually a measured quantity in the way we normally think about measurement. It's something much stranger and more subtle. It's a definition, a convention, a choice we make about how to describe the universe mathematically. Every attempt to measure one-way light speed runs into the same circular logical problem. To measure the speed, you need to know exactly when the light started its journey and exactly when it arrived at its destination. But to know these times precisely, you need synchronized clocks at both locations. And here's where the circle closes. To synchronize clocks across distance, you need to know how fast your synchronization signal travels. If that signal is light itself, you're right back where you started. It's like trying to measure the length of a ruler using the same ruler as your measuring device. The measurement becomes meaningless because it's self-referential. You're using the thing you want to measure as the tool for measuring it. This isn't just a technical challenge that better instruments might solve someday. It's a fundamental logical barrier that reveals something deep and unsettling about the nature of measurement itself. Scientists have tried countless creative approaches to get around this seemingly impossible problem. They've used rotating mirrors spinning at incredible speeds, precisely calibrated atomic clocks that lose less than 1 second every 100 million years, quantum entanglement that seems to connect particles instantaneously across vast distances, and networks of satellites orbiting Earth with atomic precision timing. Every single attempt ultimately fails for exactly the same reason. Somewhere in the measurement process, they have to make an assumption about the speed at which information travels. And that assumption makes the entire measurement circular. Consider some specific examples of these failed attempts. In the 1800s, scientists tried using rotating mirrors. They would reflect light off a rapidly spinning mirror, send it to a distant stationary mirror, and measure how much the rotating mirror had turned by the time the light returned. But this still measured the round-trip time. The assumption that light traveled equally fast in both directions was built into the calculation. More recently, physicists have tried using atomic clocks so precise they can measure time to within billionths of a second. They transport these clocks to different locations and try to synchronize them. But how do you know they're truly synchronized? You have to send a signal from one clock to the other, and that signal travels at the speed of light. To interpret the signal correctly, you need to know how long it took to travel, which brings you back to the original problem. Some scientists have proposed using quantum entanglement, where measuring one particle instantly affects its entangled partner regardless of distance. This seems to offer instantaneous communication that could bypass the light speed limitation. But quantum mechanics tells us that that while quantum correlations are instantaneous, no usable information can be transmitted faster than light. You still can't use entanglement to synchronize clocks in a way that would let you measure one-way light speed. GPS satellites carry atomic clocks and are precisely positioned in space. Some researchers have suggested using this network to measure one-way light speed. But the GPS system itself is calibrated using round-trip measurements. The satellite positions are determined by measuring round-trip times for radio signals. The system is internally consistent, but it assumes symmetric light propagation from the very beginning. Even more exotic proposals involving gravitational waves, particle accelerators, or astronomical observations all run into the same fundamental barrier. At some point in every proposed measurement, you need to know when something happened at a distant location, and that requires synchronized clocks, which brings you back to the circular problem. The history of physics is filled with brilliant minds wrestling with this paradox. Henri Poincaré, one of the greatest mathematicians and physicists of the early 20th century, recognized this problem before Einstein published his theory of relativity. Poincaré realized that simultaneity at different locations couldn't be measured directly. It had to be defined by convention. Albert Einstein, when he was developing special relativity in 1905, made this problem explicit. He wrote that we must define what we mean by simultaneity of events at different locations. We cannot measure it directly. We must choose a definition, and the most natural choice is to assume that light travels at the same speed in all directions. This choice isn't forced on us by experimental evidence. It's a free choice we make to keep our mathematics simple and our theories elegant. Einstein could have chosen any other assumption about light's directional speeds, as long as the average round-trip speed equaled the measured value. The physics would work out exactly the same way. Think about what this means for our understanding of reality. One of the most fundamental constants in physics, the speed that appears in Einstein's famous equation E equals mc squared, isn't actually a constant we've measured directly. It's a constant we've chosen to define. We've decided by convention that light travels at the same speed in all directions, because it makes our theories work nicely. But here's the truly mind-bending part. Even if we made a different choice, even if we assumed light traveled at dramatically different speeds in different directions, all of our experiments would give exactly the same results. All of our technology would work exactly the same way. GPS would still guide your car accurately. The internet would still connect computers around the world. Atomic clocks would still keep perfect time. This is because everything we can actually measure depends only on the round-trip speed of light, not the one-way speed. As long as the average of the two directional speeds equals the measured round-trip speed, the universe looks exactly the same to us. We have no way to tell the difference between a universe where light travels symmetrically and a universe where it travels at wildly different speeds in different directions. Consider the practical implications of this limitation. When Mission Control at NASA communicates with the Mars rovers, they know the round-trip communication time is about 22 minutes when Mars is at its closest approach to Earth. They send a command to the rover and wait 22 minutes for a response. But they don't actually know if the command took 11 minutes to reach Mars, with the response taking 11 minutes to return, or if the command took 20 minutes to reach Mars, with the response taking only 2 minutes to return. From NASA's perspective, both possibilities are completely equivalent. The rover responds the same way. The mission proceeds identically. There's no experiment they could perform to distinguish between these scenarios. The one-way delay is fundamentally unknowable. This applies to every aspect of space communication. When astronomers observe distant galaxies billions of light years away, they assume the light took billions of years to reach us, traveling at a constant speed. But they're making an assumption about one-way light speed. The light could have traveled much faster for most of the journey and much slower near the end, as long as the average speed equals the round-trip speed of light. Our entire understanding of the age and structure of the universe depends on this assumption. When we see a galaxy that appears to be 13 billion light years away, we assume we're seeing it as it was 13 billion years ago. But this calculation assumes symmetric light propagation. If light travels faster in some directions than others, our cosmic timeline could be completely wrong. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, provides our best evidence for the age of the universe. We observe this radiation coming from all directions and calculate that it's been traveling for 13.8 billion years. But this calculation assumes light has been traveling at the same speed in all directions for the entire history of the universe. Even more disturbing, this limitation affects our understanding of causality itself. When we say one event caused another, we implicitly assume that the cause preceded the effect. But determining the order of events at different locations requires synchronized clocks, which brings us back to the same circular problem. Imagine two stars exploding at nearly the same time in different parts of the galaxy. Did star A explode before star B, or did star B explode before star A? The answer depends on your choice of synchronization convention. With one choice, star A exploded first. With a different but equally valid choice, star B exploded first. There's no way to determine which is really correct. This challenges our most basic intuitions about time and causality. We like to think there's an objective order to events that causes precede effects in a universal sense. But the one-way speed of light problem shows us that this ordering is partially arbitrary, dependent on conventions we choose rather than facts we measure. The philosophical implications are staggering. If simultaneity is conventional rather than factual, what does this say about the nature of time itself? Is there really a universal now that extends across space? Or is our sense of simultaneous events just a useful fiction we create to make sense of the world? Some physicists and philosophers have argued that this reveals something profound about the nature of reality. Maybe time isn't the flowing river we imagine it to be. Maybe the past, present, and future all exist equally, and our sense of temporal flow is just a consequence of our limited perspective as conscious beings embedded in this four-dimensional space-time. This connects to deep questions about free will and determinism. If the future already exists in some sense, are our choices real or illusory? If simultaneity is conventional, what does it mean to say that we're making decisions now that will affect events later? The one-way speed of light problem forces us to confront the limits of human knowledge in a very direct way. There are questions about the universe that seem like they should have definite answers, but that cannot be answered through any conceivable measurement. This isn't because our instruments aren't sensitive enough, or because we haven't been clever enough in designing experiments. It's because the questions themselves run up against fundamental logical barriers built into the structure of reality. So you might be thinking, why don't we just put two perfectly synchronized clocks at different locations and measure how long light takes to travel between them? Start the timer at point A when the light begins its journey. Stop the timer at point B when the light arrives. Simple, right? Wrong. This seemingly obvious solution leads us straight into one of the most maddening circular problems in all of physics. To measure the one-way speed of light, you need synchronized clocks at both the starting point and the destination. But here's the catch that has frustrated physicists for over a century. To synchronize those clocks, you need to send a signal from one clock to the other. And what's the fastest way to send that signal? Light. But to know how long that synchronization signal took to travel, you need to know the speed of light. The very thing you're trying to measure. It's like being trapped in a logical prison with no way out. You need to know A to measure B, but you need to know B to determine A. Every attempt to break free from this circle just leads you around to the same starting point. Let's walk through exactly why this happens. Imagine you have two incredibly precise atomic clocks. the kind that lose less than 1 second every 100 million years. You want to place one in New York and one in Los Angeles to measure how long light takes to travel from coast to coast. First, you need to make sure both clocks show exactly the same time. You start with both clocks in New York, carefully synchronized to show identical times down to the nanosecond. Then you transport one clock to Los Angeles. But how do you know the clocks are still synchronized after the move? Maybe the vibrations from the airplane affected one of the clocks. Maybe the change in altitude or the different gravitational field caused a tiny shift in timing. The only way to check is to send a signal from the New York clock to the Los Angeles clock. Let's say you send a light pulse at exactly noon New York time. When the Los Angeles clock receives the signal, it reads 12:03 p.m. Does this mean the clocks are synchronized? Not necessarily. It could mean the clocks are perfectly in sync, and light took 3 hours to travel from New York to Los Angeles. Or it could mean the Los Angeles clock is running 2 hours fast, and light only took 1 hour to make the journey. Without knowing how long the light signal took to travel, you can't tell if the clocks are synchronized. But without synchronized clocks, you can't measure how long light takes to travel. You're stuck in an endless loop with no way to get the information you need. This isn't just a practical problem that better technology might solve. It's a fundamental logical impossibility built into the structure of reality itself. Even if you had perfect clocks that never gained or lost a single nanosecond, even if you could transport them without any disturbance whatsoever, you would still face the same circular problem. GPS satellites face this exact challenge on a massive scale. The global positioning system depends on incredibly precise timing. Each satellite carries atomic clocks that must be synchronized to within a few nanoseconds. But the satellites are constantly moving at 17,000 miles per hour, 20,000 kilometers above Earth. How do you keep their clocks synchronized with clocks on the ground? The answer is that you make an assumption. You assume that radio signals, which are just another form of light, travel at the same speed from ground to satellite as from satellite to ground. This assumption allows the system to work perfectly for navigation, but it doesn't solve the fundamental problem. The GPS system is internally consistent based on the assumption of symmetric light speed, but it can't verify that assumption independently. The same circular logic appears in every proposed solution. Scientists have suggested using fiber optic cables to connect distant clocks, thinking that a physical connection might avoid the synchronization problem. But signals traveling through fiber optic cables are still light signals. To interpret the timing of those signals correctly, you need to know how fast light travels through the cable. And measuring that speed brings you right back to the original circular problem. Some researchers have proposed using atomic clocks so precise that they could detect the tiny effects of relativity. Einstein's theory tells us that clocks run slightly slower in stronger gravitational fields and when moving at high speeds. Maybe these effects could be used to synchronize clocks without relying on light signals. But calculating these relativistic effects requires knowing the positions and velocities of the clocks with incredible precision. And determining positions and velocities over large distances requires measuring how long signals take to travel, which brings you back to needing the speed of light. Even more exotic proposals run into the same barrier. Some physicists have suggested using quantum entanglement, where measuring one particle instantly affects its entangled partner regardless of distance. This seems to offer a way to send information instantaneously, bypassing the light speed limitation entirely. But quantum mechanics is tricky. While quantum correlations are indeed instantaneous, extracting usable information from entangled particles still requires communication at or below the speed of light. You can't use entanglement to synchronize clocks in a way that would let you measure one-way light speed. The history of physics is littered with clever attempts to solve this problem, each one ultimately failing for the same fundamental reason. In the 1800s, scientists tried using rotating mirrors and rapidly spinning wheels with slots cut in them. They would shine light through the slots and measure how much the wheel had rotated by the time the light returned. But these experiments still measured round trip times. The assumption of symmetric light speed was built into every calculation. Armand Fizeau, a French physicist, used a rapidly rotating toothed wheel in 1849 to measure what he thought was the speed of light. He sent light through the gaps between the teeth of a spinning wheel to a distant mirror 8 kilometers away. The reflected light had to pass back through the wheel to reach his detector. By adjusting the rotation speed until the returning light was blocked by the teeth, he calculated the speed of light. But notice, this was still a round trip measurement. The light had to travel to the mirror and back. Léon Foucault improved on this method, using a rotating mirror instead of a toothed wheel. His setup was more precise, but it suffered from the same fundamental limitation. The light made a round trip journey, and the calculation assumed equal travel time in both directions. Even Albert Michelson, who won the Nobel Prize for his precise measurements of light speed, could only measure round trip times. His interferometer split light beams and sent them along different paths before recombining them. The interference patterns revealed tiny differences in the time light took to travel different routes, but every route was a round trip. The light always returned to the same point where it started. Modern experiments have pushed the precision of round-trip measurements to incredible levels. Scientists can now measure the round-trip speed of light to 15 decimal places. They use laser interferometers so sensitive they can detect changes in distance smaller than 1,000th the width of a proton. The Laser Interferometer, Gravitational Wave Observatory, LIGO, uses this technology to detect gravitational waves from colliding black holes billions of light years away. But even these incredibly sophisticated instruments can only measure round-trip light speed. The challenge becomes even more frustrating when you realize how close we seem to be to a solution. It feels like there should be some clever experimental design that could break through this barrier. After all, we can measure so many other things with incredible precision. We can weigh individual atoms, detect single photons, and manipulate quantum states. Surely we should be able to figure out something as basic as how fast light travels in one direction. But every proposed solution eventually reveals the same circular dependency. At some point in the measurement, you need to know when something happened at a distant location. And knowing when something happened at a distant location requires synchronized clocks. And synchronizing clocks requires knowing how fast your synchronization signal travels. Consider an example that seems like it might work. Suppose you have two observers, Alice and Bob, standing 1 kilometer apart. Alice turns on a laser at exactly noon according to her clock. Bob sees the light arrive and notes the time on his clock. The difference should tell you how long light took to travel from Alice to Bob, but this only works if Alice and Bob's clocks are perfectly synchronized. And verifying that synchronization requires sending a signal between them, which brings you back to the speed of light problem. You might think you could avoid this by having Alice and Bob synchronize their clocks while they're standing next to each other, then have Bob walk to his distant position. But how do you know Bob's clock didn't change during his journey? Even tiny accelerations can affect atomic clocks due to relativistic effects. To account for these effects, you need to know Bob's exact path and speed during his journey. And measuring speeds over distance requires timing, which brings you back to the synchronization problem. The circular nature of this problem reveals something profound about the structure of physical reality. It's not just a technical challenge that better instruments might overcome. It's a fundamental limitation built into the relationship between space, time, and measurement itself. This limitation has practical consequences that ripple through every aspect of modern technology. The internet relies on precisely timed data packets racing through fiber optic cables around the world. The entire system is synchronized using round-trip measurements and the assumption that light travels equally fast in both directions. If this assumption is wrong, the timing calculations that keep the internet running smoothly could be systematically incorrect. Telecommunications companies spend billions of dollars laying undersea cables to minimize communication delays between continents. They can measure the round-trip time for signals traveling through these cables with incredible precision. But they cannot directly verify that signals travel at the same speed in both directions through the cable. They assume symmetry because it makes their calculations work and their networks function properly. Even more critical systems depend on this assumption. Air traffic control uses radar and GPS to track airplanes with precision measured in meters. Nuclear power plants use precisely timed control systems to manage their reactors safely. Financial markets execute trades based on microsecond timing differences. All of these systems assume symmetric light propagation because they have no way to verify otherwise. The military implications are equally significant. Missile guidance systems use GPS and inertial navigation that depend on precise timing. Submarine navigation relies on sonar and communication systems that assume symmetric signal propagation. Satellite reconnaissance depends on precisely coordinated timing between ground stations and orbiting spacecraft. If the assumption of symmetric light speed is wrong, all of these systems could have systematic errors built into their most fundamental calculations. But perhaps the most unsettling aspect of this problem is what it reveals about the nature of scientific knowledge itself. We like to think that science is based on measurement and observation, that our theories are grounded in experimental facts. But here we have one of the most fundamental constants in physics, a number that appears in our most basic equations, and we've never actually measured it directly. The speed of light isn't just any constant, it's the conversion factor between space and time in Einstein's relativity. It determines the ultimate speed limit of the universe. It appears in the equation that tells us how matter converts to energy. And yet this crucial number is based on an assumption we cannot verify. This forces us to confront an uncomfortable truth about the limits of human knowledge. There are aspects of reality that seem like they should be directly measurable, but are fundamentally beyond our reach. Not because our instruments aren't sensitive enough, not because we haven't been clever enough in our experimental designs, but because the questions themselves run up against logical barriers built into the structure of measurement. The one-way speed of light problem is a perfect example of how the universe can be stranger than our intuitions suggest. It seems obvious that we should be able to measure how fast light travels in one direction. The concept is simple, the question is clear, and the measurement seems straightforward. But reality has a way of revealing hidden complexities that challenge our most basic assumptions about what it means to know something about the world around us. So here we are, trapped in this impossible circular problem. We can't measure the one-way speed of light without synchronized clocks, but we can't synchronize clocks without knowing how fast light travels. It's like being stuck in a logical maze with no exit. But in 1905, a young patent clerk in Switzerland named Albert Einstein found a brilliant way out of this maze. He didn't solve the problem. He did something much more radical. He made it disappear. Einstein's solution was both elegant and revolutionary. Instead of trying to measure the one-way speed of light, he simply defined it. He declared, by mathematical fiat, that light travels at the same speed in all directions. This wasn't based on experimental evidence. It couldn't be, because such evidence was impossible to obtain. It was a free choice, a convention, a decision about how to set up the mathematical framework of physics. In his 1905 paper on special relativity, Einstein wrote something that would forever change our understanding of space and time. He said that we must establish by definition what we mean by simultaneity of events at different locations. We cannot measure simultaneity directly. We must choose a definition, and the most natural choice is to assume that light travels at the same speed in all directions. Think about how radical this was. Einstein was saying that one of the most fundamental aspects of reality, the nature of time itself, is partly a matter of human choice. We don't discover what simultaneity means through careful measurement. We decide what it means by choosing a convention. And once we make that choice, the mathematics of relativity follows naturally. This approach solved the synchronization problem in the most direct way possible. If you define light to travel at the same speed in all directions, then you can synchronize distant clocks by sending light signals between them. You simply assume that the light takes the same amount of time to travel from clock A to clock B as it takes to travel from clock B to clock A. With synchronized clocks, you can then measure the one-way speed of light and confirm that it equals the value you defined it to have. But here's the beautiful and slightly unsettling part. Einstein could have chosen any other definition, and the physics would work exactly the same way. He could have defined light to travel at twice the standard speed going east and half the standard speed going west, as long as the average equaled the measured round-trip speed. All of our experiments would give identical results. All of our technology would function identically. The universe would look exactly the same to us. This reveals something profound about the nature of physical law. What we think of as fundamental constants might not be fundamental at all. They might be partly conventional, dependent on arbitrary choices we make about how to describe the world mathematically. The speed of light in Einstein's famous equation E equals mc squared isn't a discovered constant of nature. It's a defined constant that we've chosen for mathematical convenience. Einstein's synchronization procedure became the standard method used throughout physics. Here's how it works. Suppose you have two clocks, one in New York and one in Los Angeles, that you want to synchronize. You place both clocks next to each other in New York and set them to show identical times. Then you transport the Los Angeles clock to its final destination. To check that the clocks are still synchronized, you send a light pulse from New York to Los Angeles at exactly noon New York time. When the pulse arrives in Los Angeles, the Los Angeles clock should show a time that's later than noon. By exactly the amount of time you calculate, it should take light to make the journey, assuming light travels at the defined speed of light. If the Los Angeles clock shows a different time, you adjust it until it shows the correct time according to Einstein's definition. Once this adjustment is made, the clocks are synchronized according to Einstein's convention. You can then use these synchronized clocks to measure the one-way speed of light between New York and Los Angeles, and you'll find that it equals exactly the value you used in your synchronization procedure. This might seem circular, and in a sense it is. You're using an assumed light speed to synchronize your clocks, then using those synchronized clocks to measure the light speed and confirming your assumption. But Einstein realized that this circularity isn't a bug, it's a feature. It's the only way to make the problem well-defined. The genius of Einstein's approach is that it transforms an impossible measurement problem into a conventional definition problem. Instead of asking what the one-way speed of light actually is, Einstein asked what we should define it to be, and he answered that we should define it to be the same in all directions because this makes our mathematical description of the world as simple and elegant as possible. This convention has profound consequences for our understanding of space and time. With Einstein's definition, simultaneity becomes well-defined. Two events are simultaneous if they happen at the same time, according to clocks synchronized using Einstein's procedure. The concept of a universal now extending across space becomes mathematically precise. But Einstein's choice also reveals the arbitrary nature of simultaneity. With a different synchronization convention, events that seem simultaneous according to Einstein's definition might happen at different times. There's no experimental way to determine which definition is correct, because all definitions that preserve the round-trip speed of light are experimentally equivalent. This arbitrariness troubled some physicists and philosophers. Henri Poincaré, the great French mathematician and physicist, had recognized the conventional nature of simultaneity even before Einstein. Poincaré wrote that simultaneity is not discovered, but defined, and different definitions are equally valid as long as they lead to consistent mathematics. But Einstein went further than Poincaré. He built an entire theory of space and time on the foundation of his synchronization convention. Special relativity assumes that light travels at the same speed in all directions in any inertial reference frame. This assumption leads to all the famous consequences of relativity: time dilation, length contraction, the relativity of simultaneity, and the equivalence of mass and energy. The experimental success of special relativity seems to validate Einstein's choice. The theory makes predictions that have been tested to incredible precision. Particle accelerators confirm that nothing can travel faster than light. GPS satellites must account for relativistic time dilation to maintain accuracy. Nuclear reactors convert mass to energy according to Einstein's equation. But this experimental success doesn't prove that Einstein's synchronization convention corresponds to physical reality. It only proves that the convention leads to a mathematically consistent and experimentally successful theory. A different convention might lead to a different but equally successful theory. Consider what physics would look like with a different synchronization convention. Suppose we defined light to travel instantaneously from east to west and at half the standard speed from west to east, such that the average still equals the measured round-trip speed. With this definition, our synchronized clocks would show different times than they do with Einstein's convention. Events that appear simultaneous with Einstein's definition would no longer be simultaneous with this new definition. The mathematical equations of physics would look more complicated. Time dilation and length contraction would have different formulas, but all the experimental predictions would remain exactly the same. This alternative theory would be mathematically equivalent to Einstein's relativity, just expressed in a more complicated form. Physicists would get the same numerical answers to all their calculations. Engineers would design the same technologies with the same performance characteristics. The universe would behave identically from our perspective. The fact that multiple mathematical descriptions can account for the same experimental observations is a common feature in physics. In quantum mechanics, the Schrödinger picture and the Heisenberg picture give different mathematical descriptions of the same physical phenomena. In classical mechanics, Newtonian forces and Lagrangian energy methods provide different approaches to solving the same problems. But the arbitrariness in defining simultaneity goes deeper than these other examples. In quantum mechanics and classical mechanics, the different mathematical approaches are clearly equivalent and can be transformed into each other through well-defined procedures. But different simultaneity conventions lead to genuinely different statements about when events happen, with no way to determine which statements are correct. This raises deep questions about the nature of physical reality. If simultaneity is conventional, what does this say about the objectivity of time? Is there really a fact of the matter about when events happen at distant locations? Or is temporal ordering partly subjective, dependent on the conventions we choose? Some physicists and philosophers have argued that Einstein's approach reveals the conventional nature of all physical concepts. Maybe length, mass, and energy are also partly conventional, defined by our choice of measurement procedures rather than discovered through observation. This view suggests that physics doesn't describe reality as it actually is, but rather provides convenient mathematical tools for organizing our experiences and making predictions. Other thinkers have maintained that there must be objective facts about simultaneity, even if we can't measure them directly. They argue that our inability to determine the one-way speed of light reveals the limitations of human knowledge, not the absence of objective temporal relationships. In this view, there really is a correct answer to questions about simultaneity, but it's forever beyond our reach. Einstein himself seems to have evolved in his thinking about these issues. In his early work, he emphasized the operational definition of concepts like simultaneity and the importance of measurement procedures in physics. But later in life, he became more convinced that there must be objective features of reality that exist independently of our observations and conventions. The debate about the interpretation of Einstein's synchronization convention continues today. Some physicists treat it as a purely practical matter, a useful tool for making calculations without deeper significance. Others see it as revealing fundamental truths about the nature of space and time. Still others view it as evidence that our usual concepts of space and time break down at the most fundamental level. But regardless of how you interpret Einstein's convention, its practical importance is undeniable. This arbitrary choice about how to define simultaneity underlies all of modern physics. Every calculation in special and general relativity assumes Einstein's synchronization procedure. Every GPS satellite, every particle accelerator, every precision measurement in physics depends on this convention. The fact that such a fundamental aspect of our physical theories rests on an arbitrary convention might seem disturbing. We like to think that science discovers objective truths about nature, not merely useful conventions for organizing our thoughts. But Einstein's synchronization convention suggests that the boundary between discovery and convention might be more blurred than we typically imagine. This blurring of boundaries becomes even more apparent when you consider how Einstein's convention affects our understanding of causality. In Einstein's framework, cause and effect relationships are preserved. If event A can causally influence event B, then event A must occur before event B according to any valid synchronization convention. This ensures that effects don't precede their causes, which would violate our basic understanding of how the world works. But while causal ordering is preserved, the specific timing of causally unrelated events can vary depending on your choice of synchronization convention. Two events that cannot influence each other might appear simultaneous with one convention and sequential with another. This doesn't affect the physical behavior of the universe, but it does affect how we describe that behavior mathematically. The preservation of causal relationships is what makes Einstein's convention physically reasonable, even though it's mathematically arbitrary. Any synchronization convention that violates causality would lead to logical paradoxes and experimental contradictions. But within the constraint of preserving causality, there's still considerable freedom in how you define simultaneity. This freedom in defining simultaneity has practical implications for how we think about communication and information transfer. When NASA sends commands to the Mars rovers, the round-trip communication time is about 22 minutes. But NASA doesn't know whether the command takes 11 minutes to reach Mars, with the response taking 11 minutes to return, or whether the timing is asymmetric. From a practical standpoint, this uncertainty doesn't matter. The rover responds the same way regardless of how the one-way delays are distributed. But from a conceptual standpoint, the uncertainty highlights the conventional nature of our understanding of distant events. We don't really know when the rover received our command or when it sent its response. We only know the round-trip timing. This uncertainty becomes more philosophically troubling when applied to astronomical observations. When we observe light from distant galaxies, we assume it took billions of years to reach us, traveling at Einstein's defined speed. But the light could have traveled much faster for most of its journey and much slower near the end, as long as the average speed equals the round-trip speed of light. Our entire understanding of cosmic history depends on Einstein's synchronization convention. The age of the universe, the timeline of stellar evolution, the sequence of events in the early cosmos, all of these depend on assumptions about the one-way speed of light that cannot be verified experimentally. We're not just measuring the universe, we're defining how to think about it temporally. Here's where things get really mind-bending. What if Einstein had made a completely different choice? What if he had decided that light travels at twice the normal speed going north and half the normal speed going south? Or what if light moved instantaneously in one direction and took twice as long in the opposite direction? Would physics collapse into chaos? Would our technology stop working? Would the universe behave differently? The shocking answer is no. As long as the average speed equals the measured round-trip value, all of physics works exactly the same way. Every experiment gives identical results. Every piece of technology functions identically. GPS still guides your car perfectly. The internet still connects computers around the world. Atomic clocks still keep perfect time. The universe looks absolutely identical to us, regardless of how asymmetrically light might actually be traveling. This isn't just a theoretical curiosity. It's a fundamental feature of how measurement works in our universe. Everything we can actually observe depends only on the round-trip speed of light, never on the one-way speed. As long as the round-trip average remains constant, we have no way to detect any asymmetry in light's directional speeds. Let's explore this with a concrete example. Imagine we lived in a universe where light traveled at 600 million meters per second going east and only 100 million meters per second going west. The round-trip average would still be 300 million meters per second, matching our measured value. How would this affect our daily lives? Your GPS would work perfectly. The satellites would still calculate your position accurately because they only measure round-trip times to determine distances. When a satellite sends a signal to your phone, it doesn't matter if the signal takes longer going down than your phone's response takes going back up. The total round-trip time determines the distance calculation, and that remains unchanged. Internet communication would function normally. When you send an email from New York to London, the data packets might take longer traveling east across the Atlantic than the acknowledgement packets take traveling west. But your email would still arrive correctly and in the same amount of total time. The web pages would load at the same speed because they depend on round-trip communication times. Even more surprisingly, all the fundamental equations of physics would give exactly the same numerical predictions. Einstein's field equations of general relativity would produce identical results for the curvature of space-time around massive objects. Quantum field theory calculations would yield the same probabilities for particle interactions. Nuclear fusion in the sun would proceed at the same rate, producing the same amount of energy. This equivalence exists because of a deep mathematical principle discovered by philosophers and physicists studying the foundations of relativity. It's related to something called Reichenbach's epsilon parameter, named after the German philosopher Hans Reichenbach, who explored these ideas in the 1920s. Reichenbach showed that you can parameterize different synchronization conventions using a single number, epsilon, that can range from 0 to 1. Einstein's standard convention corresponds to epsilon equals 1/2, meaning light travels at equal speeds in opposite directions. But you could choose epsilon equals 0, meaning light travels instantaneously in one direction and at twice the normal speed in the opposite direction. Or epsilon equals 1, meaning light travels at twice the normal speed in one direction and instantaneously in the opposite direction. Every choice of epsilon leads to a different mathematical description of the same physical reality. The equations look different, the coordinates transform differently, and the timing of events changes. But all the observable predictions remain identical. This isn't just a mathematical curiosity. It reveals something profound about the relationship between mathematical description and physical reality. Consider what this means for space exploration. When NASA communicates with the Voyager probes, now traveling beyond the edge of our solar system, the round-trip communication time is over 40 hours. Mission controllers send a command and wait nearly a full day for a response. But they don't know if the command takes 20 hours to reach Voyager, with the response taking 20 hours to return, or if the timing is completely asymmetric. The command could take 36 hours to reach Voyager, with the response taking only 4 hours to return. Or the command could take 4 hours to reach Voyager, with the response taking 36 hours to return. From NASA's perspective, all these possibilities are indistinguishable. The probe responds the same way, the mission proceeds identically, and the scientific data is equally valid. This uncertainty applies to every aspect of space communication. When the Mars rovers send photographs back to Earth, we assume the radio signals carrying the image data travel at a constant speed. But the signals could travel much faster for most of the journey and much slower near the end, or vice versa. The photographs would arrive at the same time and contain the same information regardless of how the one-way delays are distributed. The same principle applies to astronomical observations that probe the deepest mysteries of the universe. When the Hubble Space Telescope observes distant galaxies, it measures their redshift to determine how fast they're moving away from us. This measurement tells us about the expansion of the universe and the existence of dark energy. But the measurement assumes that light from those galaxies traveled to us at Einstein's defined speed. If light actually travels asymmetrically, the galaxies could be much closer or much farther away than we calculate. They could be moving toward us or away from us at very different speeds than we measure. Our entire understanding of cosmic distances and the expansion rate of the universe could be systematically wrong. But we would have no way to detect this error because all our measurements depend on round-trip light speeds. The cosmic microwave background radiation presents an even more striking example. This radiation fills all of space and provides our best evidence for the Big Bang theory. We observe this radiation coming from all directions and calculate that it has been traveling for 13.8 billion years since the universe became transparent to light. But this calculation assumes that the radiation has been traveling at Einstein's defined speed for the entire history of the universe. If light travels asymmetrically, the radiation could have been traveling for a very different amount of time. The universe could be much older or much younger than we calculate. The entire timeline of cosmic evolution could be wrong, and we would never know because we can only measure round-trip light speeds. Even more disturbing, this uncertainty affects our understanding of the most fundamental constants of physics. The fine structure constant, which determines the strength of electromagnetic interactions, is calculated using measurements that assume symmetric light propagation. If this assumption is wrong, the fine structure constant could have a different value than we think. The masses of fundamental particles like electrons and protons are determined using experiments that involve electromagnetic interactions. These measurements assume Einstein's synchronization convention. With a different convention, the calculated masses would be different. The entire standard model of particle physics, which describes all known particles and forces except gravity, could have systematically incorrect parameters. But here's what makes this situation so philosophically troubling. Even if all our fundamental constants are wrong, even if our understanding of cosmic distances and timescales is completely incorrect, all of our technology would still work perfectly. All of our scientific predictions would still be accurate. All of our experimental observations would still be consistent. This reveals a deep disconnect between scientific truth and practical utility. We often assume that if our theories work well and our technology functions reliably, then our scientific understanding must be correct. But the one-way speed of light problem shows that this assumption can be wrong. Our theories can be practically successful while being fundamentally based on unverifiable assumptions. Consider the implications for scientific method itself. Science is supposed to be based on observation and measurement, on testing hypotheses against experimental evidence. But here we have a fundamental aspect of our theories that cannot be tested experimentally. We've simply chosen a convenient mathematical convention and built our entire understanding of space and time around it. This doesn't mean our science is wrong or useless. The mathematical framework of relativity has been incredibly successful in making predictions and guiding technological development. But it does mean that our science might be more conventional and less objective than we typically assume. Some aspects of what we call scientific knowledge might be better understood as useful mathematical tools rather than discovered truths about nature. The arbitrariness in choosing light speed conventions also affects how we think about the history of physics. We often tell the story of relativity as Einstein discovering the true nature of space and time, overturning Newton's absolute concepts and revealing the relative nature of simultaneity. But a more accurate story might be that Einstein chose a particular mathematical convention that happened to lead to simple and elegant equations. If Einstein had chosen a different convention, the mathematics of relativity would look more complicated, but the physical predictions would be identical. Future physicists might have developed different mathematical tools to handle the more complex equations. The history of physics would have unfolded differently, but the final understanding of nature would be equivalent. This raises questions about scientific progress itself. Are we discovering objective truths about reality, or are we developing increasingly sophisticated mathematical tools for organizing our observations? The success of science in making predictions and enabling technology suggests that we're learning something real about the world. But the conventional aspects of our theories suggest that this learning might be more indirect and interpretation dependent than we usually imagine. The one-way speed of light problem also affects how we think about the unification of physics. One of the great goals of modern physics is to develop a theory of quantum gravity that unifies Einstein's general relativity with quantum mechanics. But both of these theories assume Einstein's synchronization convention. If this convention is arbitrary, then the unification program might be based on arbitrary mathematical choices rather than deep truths about nature. String theory, loop quantum gravity, and other approaches to quantum gravity all assume that light travels at the same speed in all directions. They build elaborate mathematical structures on this foundation. But if the foundation is conventional rather than factual, then these theories might be exploring mathematical possibilities rather than physical realities. This doesn't invalidate these research programs. Even if the mathematical structures are partly conventional, they might still reveal important truths about the logical consistency of physical theories and the mathematical relationships between different phenomena. But it does suggest that we should be more humble about the ontological status of our most fundamental theories. The practical implications of this uncertainty extend beyond pure science into engineering and technology. When engineers design communication systems, they assume symmetric signal propagation because it makes their calculations simpler and their systems more reliable. But they're making an assumption that cannot be verified independently. High-speed trading systems in financial markets execute millions of transactions per second based on tiny timing differences. These systems assume that data travels at the same speed in both directions through fiber optic networks. If this assumption is wrong, it could affect the fairness of electronic trading. Orders that appear simultaneous might actually have arrived at different times. Aviation systems present even more critical applications. Air traffic control uses radar and GPS to track aircraft with precision measured in meters and seconds. These systems assume symmetric signal propagation. Any systematic error in timing could affect aviation safety, causing aircraft to appear farther apart than they actually are. The global positioning system itself represents perhaps the most widespread technological dependence on Einstein's synchronization convention. GPS satellites broadcast precisely timed signals that allow receivers to calculate their position. The entire system assumes that radio signals travel at the same speed from satellites to receivers as from receivers to satellites. If this assumption is wrong, GPS could have systematic errors that affect not just navigation, but also scientific experiments that depend on precise positioning. Geological surveys, earthquake monitoring, and climate research all use GPS for precise measurements. Systematic errors in GPS timing could propagate through all these applications. affecting our understanding of Earth processes. But perhaps the most profound implication of the one-way speed of light problem is what it reveals about the nature of physical reality itself. We like to think that the universe has definite properties that exist independently of our observations and conventions. But the arbitrariness in defining light speed suggests that some aspects of reality might be genuinely conventional, dependent on choices we make rather than facts we discover. This doesn't mean that everything in physics is arbitrary. The round-trip speed of light is definitely measured, not chosen. The laws of thermodynamics, the conservation of energy and momentum, the quantization of electric charge, these are all discovered features of nature. But the one-way speed of light seems to occupy a strange middle ground between discovered fact and chosen convention. Understanding this middle ground might be crucial for making progress on the deepest questions in physics. As we push toward theories of quantum gravity and attempts to understand the nature of space-time at the smallest scales, the conventional aspects of our current theories might become more important. We might need to distinguish more carefully between the mathematical tools we use to describe nature and the objective features of nature itself. Let's bring this abstract problem down to Earth, or rather, from Earth to Mars and back. Right now, as you're watching this, there are rovers crawling across the Martian surface, robotic explorers millions of kilometers away from home, waiting for instructions from mission control. When NASA wants to tell these rovers to turn left, drill a rock sample, or take a photograph, they face the one-way speed of light problem in the most practical way imaginable. The round-trip communication time between Earth and Mars varies dramatically as the planets orbit the Sun. When Mars is at its closest approach to Earth, about 55 million kilometers away, radio signals take roughly 6 minutes to travel from Earth to Mars and another 6 minutes to return. When Mars is on the opposite side of the Sun from Earth, at maximum distance of about 400 million kilometers, the round-trip time stretches to over 40 minutes. Mission controllers at NASA's Jet Propulsion Laboratory know these round-trip times with incredible precision. They can predict exactly when to expect a response to any command they send. But here's what they don't know and can never know. They have no idea whether their command takes exactly half the round-trip time to reach Mars, or whether the timing is completely asymmetric. When Mars is at closest approach and the round-trip time is 12 minutes, NASA assumes their commands take 6 minutes to reach the rovers, and the responses take 6 minutes to return. But the command could take 11 minutes to reach Mars with the response taking only 1 minute to return. Or the command could take 1 minute to reach Mars with the response taking 11 minutes to return. From NASA's perspective, all these possibilities are completely indistinguishable. Think about what this means for the daily operations of Mars exploration. Every single day, mission planners upload detailed instruction sequences to the rovers. These sequences tell the rovers where to drive, which rocks to analyze, which photographs to take, and when to communicate back to Earth. The entire mission timeline is built around assumptions about communication delays that cannot be verified. The rovers themselves are programmed to operate autonomously for most of each Martian day because the communication delays make real-time control impossible. But the boundaries between autonomous operation and Earth-based control depend entirely on assumptions about one-way light speed. If signals actually travel much faster from Earth to Mars than from Mars to Earth, the rovers could be getting commands much sooner than mission controllers realize. This uncertainty has profound implications for the scientific data returned by Mars missions. When the rovers discover something interesting, like evidence of ancient water or unusual rock formations, they transmit their findings back to Earth. Scientists analyze this data and often want to gather additional information by sending new commands to investigate further. But the scientists don't know when the rover actually made its discovery. They know when they received the data on Earth, and they know the round-trip communication time, but they can't determine the one-way delay from Mars to Earth. The discovery could have happened much earlier or much later than they calculate, depending on how the one-way delays are distributed. This timing uncertainty affects how scientists interpret the geological and atmospheric data from Mars. Many Martian phenomena, like dust storms, temperature changes, and seasonal variations, evolve on timescales comparable to the communication delays. If the one-way delays are highly asymmetric, scientists could be systematically misunderstanding the timing of these processes. Consider the search for life on Mars, one of the primary goals of recent rover missions. If scientists discover chemical signatures that might indicate biological activity, they need to understand the timing of these observations to interpret their significance. Biological processes often involve rapid changes in chemical concentrations that could be missed or misunderstood if the communication timing is asymmetric. The problem becomes even more complex when multiple spacecraft are operating simultaneously around Mars. NASA currently has several rovers on the Martian surface and multiple orbiters circling the planet. These spacecraft often coordinate their observations to study the same phenomena from different perspectives, but this coordination depends on synchronized clocks and assumptions about communication delays that cannot be verified independently. When an orbiter observes a dust storm from above while a rover measures the storm's effects on the surface, scientists want to correlate these observations precisely in time. But the correlation depends on assumptions about the one-way speed of light between different spacecraft and between Mars and Earth. If these assumptions are wrong, the scientific conclusions could be systematically incorrect. The uncertainty extends to every aspect of interplanetary communication. When NASA sends software updates to the rovers, the updates must be transmitted in carefully timed sequences to avoid corrupting the rover's computer systems. The timing calculations assume symmetric light propagation. If this assumption is wrong, the software updates could arrive at different times than expected, potentially causing system failures. Navigation presents another critical application, where one-way light speed uncertainty matters. The rovers use a combination of Earth-based tracking and onboard navigation systems to determine their precise positions on Mars. The Earth-based tracking involves measuring the round-trip time for radio signals, but interpreting these measurements requires assumptions about one-way propagation delays. If light travels asymmetrically between Earth and Mars, the calculated rover positions could be systematically incorrect. This could affect mission planning, scientific sampling strategies, and even rover safety. A rover that appears to be safely positioned away from hazardous terrain might actually be closer to danger than mission controllers realize. The same navigation uncertainty affects orbital mechanics calculations for spacecraft traveling between planets. When NASA launches a mission to Mars, the spacecraft follows a precisely calculated trajectory that takes advantage of the planet's orbital motions to minimize fuel consumption and travel time. These trajectory calculations assume that navigation signals travel at Einstein's defined speed in all directions. If the one-way speed of light is asymmetric, the calculated spacecraft positions could be wrong throughout the journey. Course corrections might be applied at the wrong times or in the wrong directions. The spacecraft could arrive at Mars with systematic errors in its position and velocity that affect the success of orbital insertion or landing operations. The European Space Agency faces similar challenges with their Mars missions. The ExoMars rover program involves coordination between European ground stations, orbiting spacecraft, and surface rovers. All of this coordination depends on timing calculations that assume symmetric light propagation. Any asymmetry in the one-way speed of light could affect the mission's scientific objectives and operational efficiency. Future Mars missions will face even greater challenges as human exploration becomes a reality. When astronauts eventually land on Mars, they will need to coordinate their activities with mission control on Earth in ways that rovers cannot. Human reflexes and decision-making capabilities could potentially take advantage of asymmetric communication delays if the delays are shorter in one direction than the other. But astronauts would also face new safety challenges, if communication timing is uncertain. Emergency situations might require rapid coordination between Mars and Earth. If the one-way delays are highly asymmetric, emergency communications could take much longer or much shorter than expected, affecting the ability to respond appropriately to dangerous situations. The psychological effects on astronauts could also be significant. The isolation of Mars is partly defined by the communication delays that separate astronauts from their families and colleagues on Earth. If these delays are asymmetric, the sense of isolation might be greater or lesser than expected, depending on which direction experiences longer delays. Beyond Mars, the one-way speed of light problem affects every deep space mission. The Voyager probes, launched in 1977, are now traveling through interstellar space more than 20 billion kilometers from Earth. Communication with these spacecraft takes over 20 hours each way, but NASA doesn't know how the one-way delays are distributed within that round-trip time. The New Horizons spacecraft, which flew by Pluto in 2015, faces similar communication challenges. When the spacecraft transmitted its stunning images of Pluto back to Earth, the signals took over 4 hours to make the journey, but the actual timing of when the images were captured depends on assumptions about one-way light speed that cannot be verified. These timing uncertainties affect the scientific interpretation of data from the outer solar system. Many phenomena in the outer planets and their moons, like volcanic activity on Jupiter's moon Io or geysers on Saturn's moon Enceladus, evolve on timescales that are comparable to communication delays. If the one-way speed of light is asymmetric, scientists could be misunderstanding the timing and evolution of these processes. The Cassini mission to Saturn, which ended in 2017, provides a perfect example of how communication timing affects scientific discovery. The spacecraft observed complex interactions between Saturn's rings and moons, phenomena that often change rapidly compared to the communication delays. The scientific interpretation of these observations depends entirely on assumptions about when the observations actually occurred relative to when they were received on Earth. Future missions to the outer solar system will push these challenges even further. Proposed missions to Uranus and Neptune would involve communication delays of several hours each way. The Europa Clipper mission, scheduled to explore Jupiter's moon Europa, will face communication delays of over an hour. In all cases, the scientific interpretation of data will depend on unverifiable assumptions about one-way light speed. The problem extends beyond robotic exploration to astronomical observations of distant objects. When the James Webb Space Telescope observes galaxies billions of light years away, it's looking back in time to see the universe as it was in the distant past. But the calculation of how far back in time depends entirely on assumptions about the one-way speed of light. If light travels asymmetrically, the observed galaxies could be much closer or much farther away than calculated. They could have existed at very different times in cosmic history than astronomers believe. Our entire understanding of galaxy formation and evolution could be systematically incorrect because it's based on timing calculations that assume symmetric light propagation. The cosmic microwave background radiation, observed by satellites like Planck and WMAPI, provides our most precise measurements of the universe's age and composition. But these measurements assume that the radiation has been traveling at Einstein's defined speed for nearly 14 billion years. If the one-way speed of light has been asymmetric throughout cosmic history, our fundamental understanding of cosmology could be wrong. Even more intriguingly, the one-way speed of light problem could affect the search for extraterrestrial intelligence. SETI researchers monitor radio signals from space, looking for artificial transmissions that might indicate the presence of alien civilizations. When they detect interesting signals, they calculate the distance to their source based on assumptions about light speed. If the one-way speed of light is asymmetric, alien signals could be coming from much closer or much farther away than calculated. The apparent timing of alien transmissions could be systematically shifted, affecting our understanding of when the signals were sent and how advanced the transmitting civilization might be. The search for extraterrestrial intelligence also involves sending our own signals into space, hoping that alien civilizations might detect them and respond. Projects like the Arecibo message, sent toward the globular cluster M13 in 1974, assume that the signal will travel at a constant speed. But if the one-way speed of light is asymmetric, the signal could arrive much earlier or much later than expected. If aliens exist and they face the same one-way speed of light problem that we do, their understanding of our solar system and the timing of our transmissions could be just as uncertain as our understanding of their signals. The entire framework for interstellar communication depends on assumptions that cannot be verified by either side of the conversation. This uncertainty even affects how we think about the possibility of faster-than-light communication or travel. Science fiction often imagines technologies that could bypass the light speed limitation, enabling instantaneous communication across vast distances. But if we don't actually know the one-way speed of light, we can't be certain what the true limitation is. The one-way speed of light could already be instantaneous in one direction. If so, we might already have a form of faster-than-light communication without realizing it. Alternatively, the one-way speed could be much slower than we think in the directions we most want to communicate, making interstellar communication even more challenging than we currently believe. The practical implications of the one-way speed of light problem extend into every aspect of space exploration and astronomy. From daily rover operations on Mars to the search for life in the universe, our understanding of cosmic distances and timing depends on assumptions that cannot be verified through measurement. We're not just exploring space, we're exploring our assumptions about the nature of space and time themselves. Stop for a moment and think about this very instant. Right now, as you process these words, what else is happening in the universe? Is someone on the International Space Station looking down at Earth at this exact same moment? Is a rover on Mars taking a photograph of the Martian sunset right now? Is light from a distant star just beginning its journey toward Earth in this precise instant? Our intuition tells us that there must be a universal now, a cosmic moment that extends across all of space. We imagine that somewhere in the universe, there's a master clock that defines simultaneity for everything. But the one-way speed of light problem reveals that this intuition might be completely wrong. The concept of now across distance might be nothing more than a useful fiction we've created to make sense of a universe that's far stranger than we imagine. Einstein's theory of relativity already shattered our naive notions of absolute simultaneity. Even with his standard synchronization convention, observers moving at different velocities disagree about which events happen at the same time. What one observer considers simultaneous, another observer sees as sequential. The relativity of simultaneity is one of the most mind-bending consequences of Einstein's theory. But the one-way speed of light problem goes even deeper. It suggests that even for observers at rest relative to each other, the concept of simultaneity might be arbitrary. Even if you and your friend are sitting perfectly still in the same room, you might disagree about whether two distant events happened at the same time, depending on which synchronization convention you choose to use. Let's explore this with a concrete example. Imagine two events happening in space. Event A is a supernova explosion in the Andromeda Galaxy, 2.5 million light-years away. Event B is a gamma-ray burst in a galaxy in the opposite direction, also 2.5 million light-years away. Both events send light toward Earth, and both light signals arrive at our telescopes at exactly the same time. With Einstein's standard synchronization convention, we would conclude that both events happen simultaneously. 2.5 million years ago. The light from both events traveled the same distance at the same speed, so they must have started their journeys at the same time. This seems perfectly reasonable and matches our intuitive understanding of simultaneity. But now consider a different synchronization convention. Suppose we define light to travel twice as fast when coming from the direction of Andromeda and half as fast when coming from the opposite direction. With this convention, the supernova in Andromeda happened much more recently than the gamma-ray burst in the other galaxy. The events that seemed simultaneous with Einstein's convention are now separated by millions of years. Which description is correct? There's no experiment you could perform to determine the answer. Both conventions make identical predictions about what you observe on Earth. Both describe the same physical reality using different mathematical frameworks. The timing of distant events becomes a matter of convention rather than fact. This arbitrariness in simultaneity has profound implications for how we think about the nature of time itself. We typically imagine time as flowing like a river, carrying all of existence forward from past to future. We think of the present moment as a universal now that encompasses everything happening simultaneously throughout the universe. But if simultaneity is conventional, this picture of time might be fundamentally incorrect. Some physicists and philosophers have argued that the conventional nature of simultaneity points toward a block universe model of time. In this view, past, present, and future all exist equally. Time doesn't flow. It's more like a landscape that we move through. What we call the present moment is just our particular location in this four-dimensional space-time landscape. The block universe model eliminates the special status of the present moment. There's no universal now because there's no objective way to define simultaneity across space. Different synchronization conventions correspond to different ways of slicing through the block universe, but all slices are equally valid. The passage of time becomes a subjective experience of conscious observers rather than an objective feature of reality. This view has disturbing implications for how we think about free will and moral responsibility. If the future already exists in the same sense that the past exists, are our choices real or illusory? If there's no objective present moment, what does it mean to say that we're making decisions now that will affect events later? Einstein himself struggled with these questions throughout his life. In a famous letter to the family of his friend Michel Bessot, Einstein wrote that for physicists who believe in relativity, the distinction between past, present, and future is only a stubbornly persistent illusion. Yet Einstein also maintained that we must act as if our choices matter, even if the ultimate nature of time remains mysterious. The conventional nature of simultaneity also affects how we think about consciousness and subjective experience. Our sense of being conscious in the present moment feels immediate and undeniable. But if simultaneity is arbitrary, what does it mean to be conscious now rather than at some other time? How can subjective experience have a definite temporal location if temporal locations are partly conventional? These questions become even more puzzling when we consider the possibility of conscious beings in other parts of the universe. If there are intelligent aliens in distant galaxies, are they experiencing their present moment at the same time as us? The answer depends entirely on which synchronization convention we choose. With one convention, alien civilizations might be experiencing their now simultaneously with ours. With another convention, their now might be millions of years in our past or future. This relativity of simultaneity could affect how we think about the search for extraterrestrial intelligence. When SETI researchers detect interesting radio signals from space, they calculate when the signals were transmitted based on assumptions about light speed. But if simultaneity is conventional, the concept of when the aliens sent their message becomes ambiguous. The aliens themselves would face the same problem when interpreting signals from Earth. They wouldn't know when we actually transmitted our messages because they can't measure the one-way speed of light between their location and ours. The entire temporal framework for interstellar communication rests on arbitrary synchronization conventions. The problem extends to every aspect of astronomy and cosmology. When we observe distant galaxies, we assume we're seeing them as they were billions of years ago, when their light began its journey toward Earth. But this assumption depends entirely on Einstein's synchronization convention. With a different convention, we might be seeing these galaxies as they were at very different times in cosmic history. Our understanding of the timeline of cosmic evolution, from the Big Bang to the formation of stars and galaxies, to the eventual heat death of the universe, all depends on assumptions about simultaneity that cannot be verified observationally. The entire narrative of cosmic history might be partly conventional, dependent on arbitrary choices about how to define temporal relationships across vast distances. Consider the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. This radiation provides our best evidence for the early universe and allows us to calculate that the universe is 13.8 billion years old. But this calculation assumes that the radiation has been traveling at Einstein's defined speed since the universe became transparent to light. If the one-way speed of light has been different throughout cosmic history, the radiation could have been traveling for a very different amount of time. The universe could be much older or much younger than we calculate. The entire timeline of cosmic evolution, from nucleosynthesis in the first few minutes after the Big Bang to the formation of the first stars and galaxies, could be shifted by billions of years. The uncertainty extends to our understanding of the ultimate fate of the universe. Cosmologists predict that the universe will continue expanding forever, with stars eventually burning out and black holes slowly evaporating through Hawking radiation. But these predictions depend on calculations of cosmic distances and timescales that assume symmetric light propagation. If the assumptions are wrong, the universe could evolve very differently than predicted. The timeline of stellar evolution, the formation and evaporation of black holes, and the approach to maximum entropy could all occur on vastly different timescales than currently calculated. Our vision of the cosmic future is built on the same unverifiable assumptions as our understanding of the cosmic past. The conventional nature of simultaneity also affects how we think about the fundamental laws of physics themselves. Many physical laws involve rates of change over time, but calculating these rates requires knowing when events occurred at different locations. If simultaneity is arbitrary, then some aspects of physical law might be arbitrary as well. Consider the law of conservation of energy, one of the most fundamental principles in physics. This law states that the total energy of an isolated system remains constant over time. But applying this law to the universe as a whole requires adding up the energy at all locations at the same time. If simultaneity is conventional, the statement of energy conservation becomes partly conventional as well. The same issue affects other conservation laws, like conservation of momentum and conservation of electric charge. These laws seem to describe objective features of reality, but their precise mathematical formulation depends on synchronization conventions that cannot be verified experimentally. The boundary between discovered physical law and chosen mathematical convenience becomes blurred. Quantum mechanics introduces additional complications to our understanding of simultaneity. The theory seems to involve instantaneous correlations between particles, regardless of the distance separating them. When you measure the spin of one particle in an entangled pair, you instantly know the spin of its partner, even if the partner is on the other side of the galaxy. This quantum non-locality appears to violate the principle that nothing can travel faster than light. But quantum mechanics tells us that while the correlations are instantaneous, no usable information can be transmitted through quantum entanglement. You can't use entangled particles to send messages or synchronize clocks in a way that would resolve the one-way speed of light problem. The existence of instantaneous quantum correlations raises deep questions about the nature of simultaneity in quantum mechanics. If entangled particles are correlated instantaneously, there seems to be a preferred notion of simultaneity built into the quantum description of reality. But this preferred notion cannot be accessed through any measurement we can actually perform. Some interpretations of quantum mechanics suggest that quantum measurements create definite outcomes from previously indefinite possibilities. If so, the moment of measurement might have special significance for defining simultaneity. But other interpretations treat quantum measurements as simply revealing pre-existing properties, eliminating any special temporal significance. The many worlds interpretation of quantum mechanics proposes that all possible measurement outcomes occur simultaneously in parallel universes. In this view, simultaneity becomes even more problematic because different parallel universes might have different synchronization conventions. The concept of a universal now becomes meaningless when now spans multiple realities. These quantum complications suggest that the problem of simultaneity might be even deeper than the classical one-way speed of light problem indicates. Even if we could somehow resolve the synchronization problem for classical physics, quantum mechanics might introduce new forms of temporal ambiguity that cannot be eliminated through any choice of convention. The philosophical implications of all these uncertainties are staggering. Our most basic concepts about the nature of time and causality rest on assumptions that cannot be verified through measurement. The temporal structure of reality, which seems so fundamental to our experience and understanding, might be partly arbitrary, dependent on conventions we choose, rather than facts we discover. This doesn't mean that time is completely illusory or that temporal relationships don't matter. Local causality is preserved regardless of which synchronization convention we choose. Cause and effect relationships between nearby events remain well defined, but the global structure of time across the universe becomes ambiguous in ways that challenge our deepest intuitions about the nature of reality. Understanding these ambiguities might be crucial for making progress on the deepest questions in physics. As we search for theories of quantum gravity that unify Einstein's relativity with quantum mechanics, the conventional aspects of simultaneity might play a crucial role. We might need to distinguish more carefully between the aspects of space-time that are objectively real and those that are artifacts of our chosen mathematical description. The one-way speed of light problem forces us to confront the possibility that some aspects of reality are forever beyond direct measurement, not because of practical limitations, but because of fundamental logical constraints. The nature of simultaneity across distance might be one of those aspects, revealing the limits of what it means to have scientific knowledge about the universe we inhabit. What if the one-way speed of light problem isn't just an annoying limitation of measurement? What if it's actually a clue pointing towards something deeper, something that could revolutionize our understanding of space, time, and reality itself? Throughout the history of physics, the most profound breakthroughs have often come from taking seemingly impossible problems seriously, from recognizing that what appears to be a limitation might actually be nature trying to tell us something important. The most successful theories in physics have emerged from grappling with paradoxes and impossibilities. When Maxwell's equations predicted that light travels at a constant speed, regardless of the motion of its source, this seemed impossible based on our everyday experience with moving objects. But taking this impossibility seriously led Einstein to special relativity and a complete revolution in our understanding of space and time. When physicists discovered that atoms should collapse according to classical physics, this crisis led to the development of quantum mechanics. When they found that the expansion of the universe appeared to be accelerating in defiance of gravity, this led to the discovery of dark energy. The one-way speed of light problem might be another such crisis, pointing toward new physics that we haven't yet imagined. Some theoretical physicists are beginning to take this possibility seriously. They're exploring whether the conventional nature of simultaneity might be masking deeper layers of space-time structure that could become accessible through new theoretical approaches or experimental techniques. These investigations are pushing into some of the most speculative and cutting-edge areas of modern physics. One promising direction involves theories of quantum gravity, the long-sought unification of Einstein's general relativity with quantum mechanics. In these theories, space-time itself might be quantized at the smallest scales, breaking down into discrete units rather than forming a smooth continuum. If space-time is quantized, the conventional nature of simultaneity might reflect our ignorance of the underlying quantum structure. Loop quantum gravity, one of the leading approaches to quantum gravity, suggests that space and time are built from tiny loops and networks at the Planck scale, about 10 to the minus 35 meters. At these incredible small distances, the smooth space-time of Einstein's theory gives way to a discrete, granular structure. The synchronization conventions that seem arbitrary at large scales might be determined by the specific structure of this quantum space-time foam. In loop quantum gravity, the flow of time itself emerges from the dynamics of these quantum networks. Time isn't fundamental, but rather emerges from more basic quantum processes. If this view is correct, the one-way speed of light problem might reflect the fact that time, as we understand it, doesn't exist at the most fundamental level of reality. This could explain why simultaneity appears conventional. What we call the one-way speed of light might be a higher-level description that emerges from underlying quantum processes that don't respect our classical notions of space and time. The impossibility of measuring one-way light speed directly might reflect the fact that the concept itself doesn't correspond to anything fundamental in the quantum structure of space-time. String theory, another approach to quantum gravity, offers different but equally radical possibilities. In string theory, the fundamental constituents of reality are tiny vibrating strings rather than point particles. These strings exist in higher dimensional spaces, with some dimensions curled up so small that we can't detect them directly. The extra dimensions of string theory could potentially provide new ways to think about simultaneity and light propagation. What appears to be light traveling through three-dimensional space might actually be strings vibrating through higher dimensional spaces. The one-way speed of light in our three-dimensional world might be determined by the geometry of these extra dimensions. Some string theorists have speculated that the conventional nature of simultaneity might reflect our limited perspective on higher dimensional reality. From the perspective of beings who could perceive all the dimensions, simultaneity might be well defined. Our inability to measure one-way light speed might simply reflect our confinement to a lower dimensional subset of the full reality. Emergent gravity theories offer yet another perspective on the one-way speed of light problem. These theories suggest that gravity and space-time are not fundamental, but rather emerge from more basic quantum information processes. In this view, Einstein's equations of general relativity are like the laws of thermodynamics, valid at large scales, but breaking down when you probe the underlying microscopic structure. If space-time is emergent rather than fundamental, the speed of light might also be emergent, arising from the statistical behavior of underlying quantum information processes. The one-way speed of light problem might reflect the fact that we're trying to apply concepts from emergent physics to more fundamental levels where those concepts don't have clear meaning. Erik Verlinde, a Dutch theoretical physicist, has developed theories where gravity emerges from quantum entanglement and information theory. In his approach, the geometry of space-time itself is determined by the entanglement structure of quantum information. The conventional nature of simultaneity might reflect our ignorance of this deeper informational structure. Causal set theory presents another radical possibility. This approach suggests that space-time is fundamentally discrete, made up of individual events connected by causal relationships. In causal set theory, simultaneity between causally disconnected events might genuinely be undefined, not just unmeasurable. If causal set theory is correct, the one-way speed of light problem might be revealing a fundamental truth about the nature of reality. Events that cannot causally influence each other might not have a well-defined temporal relationship. Our inability to synchronize distant clocks might reflect the fact that distant simultaneity is genuinely meaningless rather than simply unmeasurable. These theoretical possibilities are still highly speculative, but they're beginning to suggest experimental approaches that might shed new light on the one-way speed of light problem. Some researchers are exploring whether violations of Einstein's synchronization convention might be detectable in extreme environments where quantum gravitational effects become important. Near black holes, where gravity is extremely strong and space-time is highly curved, the usual assumptions about light propagation might break down. The intense gravitational fields might create preferred directions in space-time that could affect the one-way speed of light. Observations of light behavior near black holes might reveal deviations from Einstein's synchronization convention. The Event Horizon Telescope, which captured the first image of a black hole in 2019, might eventually have the resolution to detect such effects. Future space-based telescopes could observe light behavior in even more extreme gravitational environments, potentially revealing violations of synchronization symmetry. Gravitational wave detectors like LIGO and Virgo might also provide new ways to probe the one-way speed of light problem. These instruments measure tiny distortions in space-time caused by accelerating massive objects. The precise timing of gravitational wave signals depends on assumptions about light propagation that might be testable in extreme gravitational environments. When black holes collide and merge, they create some of the most extreme conditions in the universe. The space-time around colliding black holes is so violently distorted that normal assumptions about geometry and causality might break down. Careful analysis of gravitational wave signals from these events might reveal subtle violations of Einstein's synchronization convention. Particle accelerators might provide another way to probe the fundamental nature of simultaneity. When particles are accelerated to nearly the speed of light, they experience extreme time dilation and length contraction effects. In these extreme relativistic conditions, subtle violations of synchronization symmetry might become detectable. The Large Hadron Collider at CERN accelerates protons to energies of 13 trillion electron volts, creating conditions that existed only moments after the Big Bang. In these high-energy collisions, quantum gravitational effects might become important, potentially affecting the behavior of light and the nature of simultaneity. Future particle accelerators with even higher energies might probe physics at the Planck scale, where quantum gravitational effects become dominant. At these energies, the discrete structure of space-time predicted by quantum gravity theories might become directly observable, potentially resolving the one-way speed of light problem. Cosmological observations might also provide clues about the nature of simultaneity on the largest scales. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a snapshot of the universe when it was only 380,000 years old. Subtle patterns in this radiation might reveal information about the fundamental structure of space-time. Future cosmic microwave background missions with greater sensitivity might detect deviations from Einstein's synchronization convention that occurred in the early universe. If simultaneity is determined by quantum gravitational effects, these effects might have left observable signatures in the patterns of the cosmic microwave background. The search for dark matter and dark energy might also be relevant to the one-way speed of light problem. These mysterious components make up 95% of the universe, but interact only weakly with ordinary matter and light. If dark matter and dark energy affect the structure of space-time, they might also affect the propagation of light in ways that violate Einstein's synchronization convention. Some theorists have speculated that dark energy might be related to the quantum structure of space-time itself. If so, the acceleration of cosmic expansion caused by dark energy might be connected to the conventional nature of simultaneity. Understanding dark energy might require understanding the fundamental nature of space and time. Laboratory experiments are also pushing into regimes where quantum gravitational effects might become detectable. Experiments with ultra-cold atoms and quantum condensates can create artificial spacetimes with properties that mimic black holes and other extreme gravitational environments. These analog systems might reveal new insights into the nature of simultaneity and light propagation. Precision tests of special and general relativity continue to push the boundaries of what's experimentally accessible. Tests of the isotropy of light speed, the constancy of fundamental constants, and the equivalence principle are reaching unprecedented levels of precision. While these tests haven't yet revealed violations of Einstein's theories, they're approaching the sensitivity levels where quantum gravitational effects might become detectable. Quantum information experiments might also provide new approaches to the simultaneity problem. Quantum entanglement creates instantaneous correlations between particles, seemingly violating the light speed limit. While these correlations can't be used to send information or synchronize clocks, they might reveal something about the fundamental structure of space-time. Some theorists have proposed that space-time itself might be built from quantum entanglement. If so, the patterns of entanglement in quantum systems might provide information about the underlying structure of space and time. Experiments that probe quantum entanglement across large distances might reveal new insights into the nature of simultaneity. The development of quantum computers might also open new experimental possibilities. Quantum computers can simulate quantum systems that are impossible to study directly, potentially including models of quantum spacetime. These simulations might reveal how simultaneity behaves in quantum gravitational systems. All of these possibilities remain highly speculative, and it's entirely possible that the one-way speed of light problem will never be resolved through new physics. The conventional nature of simultaneity might simply be a fundamental feature of reality that we must accept rather than explain. But the history of physics suggests that taking impossible problems seriously often leads to unexpected breakthroughs. The one-way speed of light problem shares many features with other great mysteries in physics, like the measurement problem in quantum mechanics or the information paradox in black hole physics. It reveals fundamental limitations in our current understanding while pointing toward deeper truths that we haven't yet grasped. Whether through quantum gravity, higher dimensions, emergent space-time, or entirely new theoretical frameworks, the resolution of the one-way speed of light problem might require concepts and mathematics that we haven't yet developed. But the fact that such a basic question about the nature of light and time remains unanswered suggests that there are still profound mysteries waiting to be discovered. The search for new physics motivated by the one-way speed of light problem is driving innovations in experimental technique, theoretical modeling, and mathematical analysis. These investigations are pushing the boundaries of what's possible in modern physics, potentially opening new windows into the deepest structures of reality. Even if the one-way speed of light problem never leads to revolutionary new physics, the investigation itself is revealing important truths about the nature of scientific knowledge and the relationship between theory and experiment. It's showing us the limits of what can be measured directly and the role of conventions in our most fundamental theories. But if the problem does point toward new physics, the implications could be as revolutionary as the discoveries of relativity and quantum mechanics. We might need to completely reconceptualize our understanding of space, time, causality, and the nature of physical law itself. The impossible measurement that has frustrated physicists for over a century might be the key to unlocking the next great breakthrough in our understanding of the universe. So here we are at the end of our journey into one of physics' most profound mysteries. We started with what seemed like the simplest possible question. How fast does light travel in one direction? It's a question that any curious person might ask, a question that seems like it should have a straightforward answer. After all, we live in an age where we can measure the masses of distant planets, detect gravitational waves from colliding black holes, billions of light years away, and photograph the event horizon of a black hole itself. Yet this seemingly basic question about the speed of light, one of the most fundamental constants in all of physics, remains completely unanswerable. Not because our instruments aren't sensitive enough, not because we haven't been clever enough in designing experiments, but because the question itself runs up against logical barriers built into the very structure of measurement and reality. The speed of light, that famous number 299,792,458 meters per second, isn't actually a measured quantity in the way we normally think about measurement. It's a defined quantity, a convention we've chosen to adopt because it makes our mathematical description of the universe elegant and consistent. We've built our entire understanding of space, time, and causality on this single, unverifiable assumption. Every GPS satellite orbiting overhead, every fiber optic cable carrying internet data around the world, every precision clock in every physics laboratory, all of them depend on Einstein's synchronization convention. Our entire technological civilization rests on assumptions about the nature of simultaneity that can never be tested through direct measurement. This isn't a failure of science, it's a revelation about the nature of scientific knowledge itself. We've discovered that some aspects of reality are forever beyond direct measurement, not because of practical limitations, but because of fundamental logical constraints. The one-way speed of light belongs to a strange category of questions that seem meaningful but cannot be answered through any conceivable experiment. What makes this discovery so profound is what it reveals about the relationship between mathematics and physical reality. The equations of relativity, quantum mechanics, and all our other successful theories describe the world with incredible precision. They enable us to build technologies that work with astounding reliability. They let us predict the behavior of everything from subatomic particles to entire galaxies. But these same equations rest on conventional choices about concepts like simultaneity that have no basis in direct measurement. The boundary between discovered truth and chosen convention is far more blurred than we typically imagine. Some aspects of what we call scientific knowledge might be better understood as useful mathematical tools rather than direct descriptions of reality. This doesn't mean that physics is just a matter of opinion or that all scientific theories are equally valid. The round-trip speed of light is definitely measured, not chosen. The laws of conservation, of energy and momentum, describe real constraints on how the universe behaves. Quantum mechanics makes predictions that can be tested with incredible precision. But the framework within which we interpret these measurements and predictions involves conventional elements that cannot be eliminated. The one-way speed of light problem forces us to confront fundamental questions about the limits of human knowledge. Are there aspects of reality that remain forever hidden from us? Are there truths about the universe that cannot be discovered through measurement and experiment? The answer appears to be yes, and this recognition might be crucial for making progress on the deepest problems in physics. As we search for theories of quantum gravity that might unify relativity with quantum mechanics, as we try to understand the nature of dark matter and dark energy, as we probe the fundamental structure of space and time at the smallest possible scales, we might need to be more careful about distinguishing between the aspects of our theories that describe objective reality and those that reflect our chosen mathematical conventions. The one-way speed of light problem might be pointing toward new physics that requires completely rethinking our concepts of space, time, and causality. Or it might be revealing permanent limitations in what it means to have scientific knowledge about the universe. Either possibility has profound implications for how we understand the relationship between human consciousness and physical reality. But perhaps the most important lesson from this mystery is about the nature of scientific humility. We live in an age of incredible technological capability and scientific understanding. We can manipulate individual atoms, decode the human genome, and observe the most distant galaxies in the universe. It's easy to assume that any well-posed scientific question should eventually yield to careful measurement and logical analysis. The one-way speed of light problem reminds us that this assumption might be wrong. There might be fundamental questions about the nature of reality that will forever remain beyond our reach. This doesn't diminish the value of science or the importance of continuing to push the boundaries of what we can measure and understand. But it does suggest that we should approach the universe with a sense of wonder and humility about the limits of human knowledge. In a strange way, the impossibility of measuring the one-way speed of light makes the universe more mysterious and beautiful, not less. It reveals that even our most basic concepts about time and causality rest on profound assumptions about the structure of reality. It shows us that the universe still holds secrets that challenge our deepest intuitions about the nature of existence. When you look up at the night sky, when you see light from distant stars that has traveled for years or centuries to reach your eyes, remember that you don't actually know when that light began its journey. The timing of distant events, the simultaneity of cosmic phenomena, the very concept of now extending across the universe, all of these depend on conventions we've chosen, rather than facts we've measured. This doesn't make the stars less real or their light less beautiful, but it does make the universe more mysterious. It reminds us that even in our age of scientific enlightenment, even with all our sophisticated instruments and mathematical theories, there are still profound questions about the nature of reality that we cannot answer. The speed of light, one of physics' most sacred numbers, turns out to be partly a matter of human choice. We've never measured how fast light travels in one direction, and we never will. But we've learned something perhaps even more valuable: that the universe is stranger than we imagine, that the boundary between knowledge and assumption is more complex than we thought, and that some of the deepest questions about reality might forever remain beyond our reach. In that not knowing lies a deeper insight. The universe still holds mysteries, not because we haven't looked hard enough, but because some questions reveal the fundamental limits of what it even means to know something about the world around us. And perhaps that's exactly as it should be. A universe with no remaining mysteries, no unanswerable questions, no profound limitations on human knowledge would be a much less interesting place to inhabit. The one-way speed of light will likely remain forever unmeasured, forever unknowable through direct experiment. But in wrestling with this impossibility, we've learned something profound about the nature of time, space, measurement, and reality itself. We've discovered that even our most fundamental physical concepts rest on assumptions that cannot be verified, that the universe is built on a foundation that is part discovered fact and part human convention. This mystery has taken us on a journey from the most practical concerns of GPS satellites and internet communication to the deepest questions about the nature of existence itself. It's shown us how a seemingly simple question about the speed of light opens up into questions about consciousness, free will, the reality of time, and the limits of human knowledge. And in the end, perhaps that's the most beautiful thing about this mystery. It connects the everyday world of technology and measurement to the profound philosophical questions that have puzzled humans for millennia. It shows us that physics isn't just about calculating the behavior of particles and fields, but about understanding our place in a universe that is far stranger and more wonderful than we ever imagined. The one-way speed of light remains unmeasured and unmeasurable, but in that impossibility, we found something even more valuable, a deeper appreciation for the mystery and wonder of existence itself. Some questions, it turns out, are more important for what they reveal about the nature of questioning than for any answer they might provide. And the one-way speed of light is perhaps the most profound question of this kind that physics has ever discovered.